This is a very good problem on how to calculate work done by a force. Let us understand the situation. A chain of mass m and length L rests on a rough horizontal surface. Let me draw a chain here. You'll have to excuse my diagram. Pretend that the chain is uniform. What do I mean by that? All the links are of the identical shape and size. Okay. Now, if f fraction of the chain, let's say, hangs over the edge of the table, let's say if it if the overhang is slightly greater than f fraction of the length, they're saying that the chain begins to slide off the table. Now the question is, by the time the chain slides off the table, what is the total work done by the friction forces? If you realize the friction force is varying here because the length of the chain on the table is decreasing. Okay, if the length of the chain decreases, the normal force, okay, so that is supported by the table decreases, so the friction force will decrease. So here the most important skill is to set up the required function and then integrate it. So let us go over the process here. Imagine we are taking the left edge of the chain as the origin, okay, and then let the chain slide off a distance x. So if I look at the diagram here, so we are taking this as the origin. So if we let the chain slide by distance x, again you'll have to pardon my diagram. The length here will also go down x here. So if this is x, okay, so now how do we calculate the friction force here? So to calculate the friction force, we will have to figure out the mass of the chain on the table. So if you look at the mass of the chain on the table, okay, so earlier f fraction of the chain was hanging over the edge. So here f is between 0 and 1. So f is like half or 1/3, etc. So this length on the table would be, let's say if half of the chain is hanging over the edge, half of the chain will be on the table. Okay, so if 1/3 is hanging, 1 minus 1/3, 2/3 will be on the table. So f is a number between 0 and 1. So we can say that if the length of the chain that is hanging over the edge is f into L. Okay, so let me write that L. Yeah, L. The length of the chain on the table would be 1 minus f into L. So here we said the chain moved to the right by an amount x. So this length, okay, so this length would be 1 minus f into L minus x. So here if you write down the mass of the chain on the table, it would be mass per unit length into length of the chain, which is 1 minus f into L minus x. Okay, so this let us call it as m prime. Okay, now if I look at the forces that are acting on the portion of the chain which is on the table, so let us look at the free body diagram of just the portion of the chain which is on the table. So I'm just showing you the horizontal level. Okay, so we are saying that let us consider the mass of the chain on the table is m prime. Okay, so the earth is going to apply a gravitational force of m prime g in the downward direction, and the table is going to support by applying a normal force which is equal to m prime g. Okay, so this normal force is m prime g. Okay, now in order to calculate the frictional force, we need to know the coefficient of friction. Okay, and the coefficient of friction is not given in the problem, but the good news is we can actually balance the forces by considering the situation when the chain is about to slip. So if you look at the initial given situation, we can figure out the coefficient of friction. So how do we get that? So let's say I'll do it in a different screen. Okay, so if I look at the free body diagram of the chain that is hanging over the edge of the table. Okay, so Earth is applying a force on it which is equal to mass times g. Now what is the mass of this overhanging portion? If I take mass per unit length, so that would be m by L, and then F into L is the length of the chain that is hanging over the edge. So we can write F into L, so that's mass. So if I multiply by G, I'll get the gravitational force acting in the downward direction. Now this chain is held at rest. It is about to begin, but you can say that it is almost at rest. So the tension acting in the upward direction will be equal to this gravitational force, which is we can write it as F into m into g. Now this is the same force which is trying to pull the chain to the right. The chain which is on the table that is getting pulled to the right with the help of this force. So if you take the free body diagram of the chain which is placed on the table, this is the initial scenario. So we have this tension acting to the right. Now as usual, Earth is going to apply force in the downward direction. The gravitational force is the mass of the chain on the table would be mass per unit length into the length of the chain, which is 1 minus F into L, and then I just multiply by G. Now the normal force here will be equal to this. Okay, so I think if I write down the normal force, it will be 1 minus F. Okay, so we can ignore the L here in the numerator and denominator. So 1 minus F into G. Now, because we have selected a limiting scenario where the chain is about to slip, we can say that the the friction force which is acting to the left is the maximum possible friction. So what is the value of this maximum possible friction? Again, please bear in mind the F here is fraction, and this F stands for friction force. So how do I get the maximum possible friction force here? It would be mu times normal. Okay, so if I take the force which is acting to the left and then equate it to the force that is to the right on the chain, okay, we will get the value of mu. So here this is mu times normal. So if I substitute mu into 1 minus F into m into g, So that is equal to the tension force, which is F into M into G. So here the coefficient of friction is F over 1 minus F. Now that we have the coefficient of friction, we can proceed to calculate the work done by friction. So here the maximum possible friction force, here again the F here refers to friction, not fraction. So the maximum possible friction here is mu times normal, which is mu times M prime G. So if I assume that the left end of the chain displaces by an amount dx to the right, the work done for that tiny displacement can be written as the friction force multiplied by the amount of displacement. Since the displacement and the friction, they're in the opposite directions, the work done will be negative. So if I integrate this for the entire displacement, we should get the work done by the friction here. So here let us substitute everything here. So this is negative of friction is mu. If you look at the coefficient of friction, it is F by 1 minus F. The mass of the chain in this intermediate situation, we obtained this earlier, so mass per unit length into length of this chain, which is M by L into 1 minus F into L minus X. So if I multiply by G, okay, this is the maximum possible friction in the intermediate situation. And then if you allow the chain to displace by an amount dx, so that's the work done for the tiny displacement. But if I integrate for the entire displacement, the entire displacement is 1 minus F into L. So that was the initial length of the chain on the table. So here, if you pull the constants out of the integral, so we have F by 1 minus F is negative mg by L. So all these are constant factors, and then we just have to integrate. These are the limits of integration. Okay, so if you look at the integral is easy. Okay, so this is often the case in problems related to basic physics. The setup is difficult to obtain, the function that we need to integrate, but usually the integrals are very easy. So here the first term is constant and the second term has x. So the integral of the first term is simply constant into x, and for the second term it is x square by 2. So I am assuming that you know these basic integrals. So finally the work done is negative of F by 1 minus F into mg by L. And then if I look at the integral, so I have 1 minus F into L into x minus x square by 2. So at this point, let us substitute the limits. Okay, so here we have minus F by 1 minus F into mg by L. So if I substitute the upper limit, I think in the first term I have 1 minus F into L, so it's getting repeated. So I have 1 minus F square into L square. In the second term, okay, it is 1 minus F square into L square by 2. If I substitute the lower limit, I anyway have 0, so we can leave that out. So here if you see the numerator and the denominator, you have 1 minus F into L common everywhere, so you can ignore that. So I'll be left with F, and then from within the brackets I can pull 1 minus F out. Okay, so I will be left with mgl in the numerator and 2 in the denominator. So that's the work done by the friction forces by the time the chain slips off the table.